Welcome to the Explainer. Today, we're going to pull back the curtain on trigonometry. And you know what? It all starts not with some crazy formula, but with something super simple, just measuring a turn. So, what is trigonometry, really? I mean, what's it all about? Well, believe it or not, the best clue is right there in the name. The word itself basically gives away the entire game. If you break it down, you get trig, which means three, gon for angle, and metron, which is all about measure. Put it all together, it's literally the measurement of three-angled shapes, or as we call them, triangles. At its very core, that's all it is. Okay, but before we can start measuring the angles inside a triangle, we need a really solid way to talk about what an angle even is. And the most intuitive way, the way that really makes sense, is to think of it as a rotation, a turn. So let's build one. Imagine a single ray just sitting there, pointed in one direction. This is our anchor, our starting point. We call it the initial line. Now picture a second ray pinned down at the exact same starting point. And we start to pivot it, rotating it away from that first line, opening up a gap. This second moving ray, that's our terminal line. And that gap, that amount of rotation between the two, yep, that is the angle. So you see, an angle isn't just a static shape, it's a measure of movement. And just so we're all on the same page, the standard in math is to say that a counterclockwise turn is a positive angle. So now that we agree an angle is a turn, we need a way to measure how much of a turn it is. And it turns out there are two main languages we can use. You for sure know the first one, but the second one, that's where things get really cool. On one side, we've got degrees. This is the system we all learn in school, and it's completely human-made. We think the ancient Babylonians came up with it, probably because 360 is just a fantastic number that you can divide in so many ways. But on the other side, we have radians, and these are different. Radians aren't invented, they're discovered. They come from the very nature of what a circle is. We all know this, right? A full circle, one complete trip around, is 360 degrees. Each one of those degrees is just a tiny slice, 1/360th of the whole turn. It works perfectly fine, but it's so important to remember that that number, 360, is totally arbitrary. We just picked it. Which brings us to the big question. What in the world is a radian? Because unlike a degree, a radian isn't arbitrary at all. It's defined by the circle's own internal logic, and that's what makes it so incredibly powerful, especially in higher-level math. Okay, check out how elegant this is. Take any circle you want, big or small, doesn't matter. Find its radius. Now take that exact length, but bend it and lay it right along the edge of the circle. The angle that this curved piece makes from the center, that is exactly 1 radian. It's this beautiful, perfect link between the radius and the angle. And it's because of this natural connection that radians are the absolute go-to in fields like physics and calculus. They just make the formulas cleaner, simpler, and more elegant. You could say they're the native language of circles. All right, so since degrees and radians are just two different ways of measuring the exact same thing, there's got to be a way to translate between them, right? Of course, we need a bridge to get from one system to the other. And this, right here, this is the whole key. This is the Rosetta Stone for angles. A half turn of a circle is 180 degrees. That same exact turn is also pi radians. If you remember this one fact, 180 degrees equals pi radians, you can figure out everything else. So the actual conversion is pretty easy. To go from degrees to radians, you just multiply by pi over 180. Want to go the other way, from radians back to degrees? Just flip that fraction over and multiply by 180 over pi. So let's take a common one, like 60 degrees. Do the math, and bam, you get pi over 3 radians. Same turn, different name. Okay, so we've got our definitions, we know how to convert, but what's the point? Where does the rubber meet the road? Let's take this idea and see how it helps us solve a real, actual problem. I know you might be thinking this is all kind of abstract, but really, this is the bedrock of pretty much all modern measurement. I mean, think about ancient astronomers charting the stars, or sailors navigating the huge open ocean. They were using these exact ideas to figure out where they were and where they were going. All right, let's get our hands dirty with the real problem. Imagine you've got a circle, and you know its diameter is 50 centimeters. You then measure a piece of the edge, the arc, and it's 11 centimeters long. The puzzle is, what's the angle that arc makes back at the center of the circle? Well, the most direct way to solve this is to use radians, the circle's natural language. First, the radius is just half the diameter, so that's 25 centimeters. Then, the formula for the angle in radians is super simple. It's just the arc length divided by the radius. So we take 11, divide by 25, and we get 0.44 radians. From there, we just use our conversion formula to turn it into degrees, which gives us about 25.2 degrees. Done. And this is just a fantastic example of how powerful this is, because this exact same logic, connecting an arc, a radius, and an angle, is exactly what we do to calculate the distance between New York and London on our curved planet, or to track a satellite whipping around in orbit. It's the same math, just on a much, much bigger scale. So, if there's one thing to take away, it's this. An angle is just a turn, and we've got two ways to talk about it. The one we made up, degrees, and the one the universe gave us, radians. Knowing how to speak both languages doesn't just help you pass a math test. It gives you the fundamental tool that we've used to map our world and navigate the entire cosmos. So the next time you see a circle, just ask yourself, what else could we map?